Welcome back, everyone. I'm Michael Shields from Johns Hopkins University. I'm going to be introducing our second day of the UQPI training session. Yesterday, we focused largely on the structure of UQPI and how it's set up, the basic capabilities that you need in order to run a model with UQPI and to do some analysis with the software. Today, we're going to get into some of the more advanced capabilities. And we're going to start by talking about the inference module, and we'll spend about an hour talking about the inference module, and then we'll take about a 15-minute break after that. And then we're going to talk about three additional modules after the break. We'll talk about reliability and the capabilities that we have there, the surrogates module, and lastly, the stochastic process module for generation of stochastic processes in random fields. And just as a quick refresh from yesterday, I want to go through, for anyone who either doesn't remember from yesterday or who wasn't in attendance yesterday, I want to go through quickly the way that you can follow along through the Binder site. So if you go to the UQPI GitHub page, at the very bottom of the UQPI GitHub page, you'll see a button that says Launch Binder. If you click on that button and give it just a moment to load, that will load the repository off of GitHub, and you can use that repository. You can search through there. You can run all of the examples, and I'll show that as soon as this loads here. So you see this is our UQPI repository on GitHub. You have the source code here in all available. These are the various modules. If you come back to the home, you can go into these examples, and we'll be running several of these examples through the training session today. In particular, during the inference class, or during the inference module, we'll be discussing some of the examples in the Bayesian example here, as well as some of the others well, as well as some of the reliability examples that come in subset simulation, Taylor series, and other things. So you can follow along with these examples as we go along. And I also want to just refresh everyone that we've set up a forum for the training as well as for the software in general. So if you go to uqpi.freeforums.net, then you can see that we have a number of threads that you can add questions or comments about the software, particularly questions that relate to the training session today, new capabilities that you'd like to see implemented in UQPI, as well as some feedback on the capabilities that you're already using, or if you want to report a bug or an issue, you can do that here as well. So with that being said, I will turn it over now to Audrey Olivier, who is going to discuss the inference class. And just bear with me 1 second while I transfer over to her computer.
So good morning, everybody. Thank you for coming back. So this morning I'm going to be talking about the inference module of UQPI. So the idea behind inference is that you want to so there are two levels of inference. One, you may want to calibrate the parameters of a model given some data. And at a second level, you may want to select the model that best explains the data among a set of candidate models that you have. And so those two tasks are tasks of parameter estimation and model selection. And the inference module of UQPI has a couple of classes that allow you to do both parameter estimation and model selection. So the inference model has the following structure, as you can see here. So we have two classes that allow you to do parameter estimation, one class of maximum likelihood and one of Bayesian inference that allows you to approximate the full posterior PDF of the parameters given your data. So first I'm going to be talking about those two classes of parameter estimation. The second level of inference, as I said, is the level of model selection. And again, we have a couple of classes that allow you to do that. First, using information theoretic criteria to rank different models, or through a fully Bayesian perspective by computing the posterior probability of all your models. So here, those two model selection classes, they actually make use of the parameter estimation classes that I'm gonna describe first. Now, the one thing that is common to all of this is that you first need to define your models. So if you just do parameter estimation, you may define only one model. If you do model selection, you're going to define several models. And this is done by instantiating an object of the class model. And that's the first thing I'm going to be talking about. So there are two types of models that you can define and perform inference on within UCuPy. The first type of model is a probability model. So the idea here is that it's your data comes from a certain probability distribution that is parameterized by a parameter vector that I call theta here. So an example, you could have like a univariate Gaussian, and what you want to do, you have some data coming out of it, and what you want to do is, for example, learn the mean and the standard deviation of that probability distribution. So that's one example. So now, in order to define a model, such a model, you need to give it an input called model name. And that's going to be the string that is going to be called by the distribution class. So if you recall from yesterday, Dimitris presented the distribution class, and there is an input called this name. And model name is going to be used in that input. This distribution must have either a log PDF or a PDF method. And those should be callables that accept exactly two input parameters. Input parameters X, which is going to be the data, and params, which is going to be theta. So I'm going to show examples of that during the examples. Then the data, so in inference, we assume that you have access to some data and you want to learn from that data. Now in UCuPy, what's important is the size of the array that corresponds to that data. And for a probability model, the size of that data is it's an ND array of size n times d, when d is the dimension of the distribution. For example, if you want to learn the parameters of a two-dimensional Gaussian PDF, then d equals 2, and n is the number of samples that you have out of that distribution. So that's the first type of models that you can define in UCuPy. The second type of model is kind of a more generic type, where you have, so the probability model is shown as here. Your data is generating via a nonlinear equation, h of theta, and then you have a Gaussian error term here. So h here is defined using run model. So the idea here is that h could be basically kind of anything. And so we're gonna show some examples of that. You can basically use external codes that are just parameterized by a set of parameters, and you want to learn the parameters. So it's you can do quite a lot of things using that model. And the main input to that would be the model script. So it's a Python file ending in .py, and it's going to be an input to run model. Then the error term here is Gaussian. So for now, we assume that the error term is zero mean with a known and fixed covariance. So you can give the covariance as the input error covariance. In future versions of UCuPy, we're also gonna add some capabilities where we're gonna be able to learn the properties of that covariance. But for now, we have to assume that it's known. And now the data that you're gonna use to learn out of this model, it has to be a one-dimensional vector. So here are some additional parameters that can be defined for both types of models. So first, something that's very important is that the input n params is required. So it defines the number of parameters that you want to infer. So it's the length of that parameter vector theta. And you have to give it when you define model. Then you can define a prior for your parameter vector. This is going to be used when we call Bayesian inference capabilities of UCuPy. And the prior will be defined using, again, the distribution class. So you can define the prior name as a string, certain parameters, even copula if you have a copula on your prior. Again, this distribution must have a log PDF method or PDF method. And then both models can also take in some fixed parameters. If there are some, if your model is parameterized by a set of parameters that you know and you don't want to learn out of your data, then you can also include that. The main function of the class model is that it defines a method called log-like, which is a function that given some data and a parameter vector computes the log likelihood. So this is the log probability of the data knowing your parameter. And this function will be called by all the inference classes. So this is a summary of all the input attributes of class model. So basically the model type is what defines whether you have a probability distribution or a Python model. And so you define it's either the string PDF or the string Python. As I said, n parameters is required, as well as model name. So for example, if you have a Python model, which is the type 2 model that I was talking about, you can actually go give all the inputs to run model, because run model is going to be used to run your model. So, and then you can give the error covariance, the prior, as I said. So I've been through all those attributes before. And the output attributes of that class are, as I said, the log-like, which is a function that computes the log likelihood, and the prior, which is an instance of class distribution if you've given a prior to your model. The class model is imported as any other class in UCuPy, so you can either do a from UCuPy import inference or directly from UCuPy the inference import model, and you have to give it all the parameters that either are required or you seem necessary for defining your model. So now I'm going to show you some examples of that model. So here we go. So first, so in the example folder, actually you have to go to the Bayesian folder. It's maybe not, now I think about it, not the best name that we could have given to that folder. Inference would have been better, but so get that for now. So in the Bayesian folder, you have basically two folders here. And to start, I'm gonna just start with the simple examples that are in the folder illustrations of inference classes, and the maximum likelihood example, which is this one here. Okay. So the idea is that in those examples that I'm going to show you now, I've generated the data synthetically, and then I'm trying to learn from that data. So first I'm going to show you two examples of defining a model for a probability distribution, and then one example of using run model. So the first example is, as a very simple univariate Gaussian, for which you want to learn the mean and the standard deviation. So as always, you do the necessary imports. So from inference, we need to import model here, and I'm going to do maximum likelihood estimation later on. And from UCuPy distributions, I'm importing distribution. And so in this second box here, I'm generating the data from a univariate normal PDF. And so here, what's important is that you see the shape of the data vector that I'm using to later perform inference. And that is that I've generated 1,000 samples, and it's a univariate Gaussian. So my data vector, my data array, sorry, is 1,000 times 1 in the array. And here is simple as that to call the model. So you define a model. The model type here is PDF because it's a distribution type model. I have two parameters because I'm trying to learn both the mean and the standard deviation of that model. And then the model name is the string that's going to be called by distribution. So it's the name of the probability distribution that I'm learning from. So here it's a normal distribution. So this is the first model that I wanted to show you. Then the second one is a little bit more complicated. So here, what I'm trying to do is that I'm trying to learn the parameters that define a two-dimensional PDF that where the data is generated by having two univariate Gaussians for the marginals, and then a copula, a Gumbel copula, to create some dependency between the two dimensions. So here again, I'm just generating the data. By the way, I'm generating data using importance sampling because a distribution with copula doesn't have an Arviz method. And so you need to find another way to generate data. And one way is, for example, through importance sampling that we saw yesterday. And again, so the shape of the data here, I'm generating 5,000 samples and I'm in dimension 2. So you see the shape of the data here. And so here, so the way I define that model is again through model type PDF. Now I have 5 parameters. So I'm trying to learn the mean and standard deviation of the two marginal distributions, plus the one parameter that governs the behavior of the Gumbel copula. So in total, I have 5 parameters. And then the model name is, again, it's the string that is going to be called by distribution. So it's the name of the distribution. So here is the important part. When we call distribution with a copula, we actually give it 2 separate sets of parameters. One set of parameters for the marginals in params, and one set of parameters for the copula in copula params. So now inference itself cannot handle 2 different vectors for the parameters. The parameters have to be, you need to define a probability distribution that uses only a single vector where you have all your parameters. And so here we did this by redefining a new distribution, which I call bivariate normal Gumbel. And we did this, and so we created a new .py file. So basically, when we're gonna call distribution, it's gonna call a custom distribution. So again, Dimitris talked about that yesterday, about how to define custom distributions. And so the idea here is that you just define a new distribution where now the PDF and log PDF methods take, as I said in the introduction, exactly 2 inputs. X, which is going to be your data, and params. And params is one parameter vector that has all the 5 parameter vectors that that it needs. So again, so if you want to do something with copula, or so you need to redefine your model in this way. Okay, and the final model I wanted to go through is a Python model. So here it's a simple regression model where my nonlinear function f or h, I called it before, is a quadratic model. So it has 2 parameters, θ0 and θ1 here. Again, I'm generating data from this model. So here, first I generate data from this quadratic function, and then I add some noise to this. And here you can see that the noise I had as a covariance, as a diagonal covariance. And this error covariance here is going to be given when I define model. The shape of the data here is the thing that's important, and you can see it's a 1-dimensional vector. So I'm generating 50 samples from that model. And when I instantiate my model, so again, I call model, I have two parameters here, theta 0, theta 1. And my model type is Python now. It's the type 2 model that I was talking about. And what I need to give it are the inputs to run model. So it's going to be model script and model object name. Again, this refers to the inputs of run model that we saw yesterday. And basically, that means that I defined a .py function that I can show you now. So it has several models because I'm going to do model selection later, but basically the one I'm calling is model quadratic here. So you can see that my object model name is model quadratic. So this is defined in the .py file that I'm showing you here. And so this refers to, again, I'm referring you to run model for you to get back to that. And I define an error covariance, which is, now I know it because I self-generated the data. So I know what my error covariance is. Okay, so this is how to define a model. So that's the most important part of inference, because you're gonna have to do that every time you perform inference. Okay, so the first, so now we actually get into inference, and this is the first class for doing parameter estimation, and this is through maximum likelihood estimation. So what maximum likelihood estimation does is that it finds the parameters that maximizes the likelihood, so the probability of the data knowing your parameter. In UCuPy, what you need to give to the ML estimation class is an instance of class model, which is your model, and then some data. And the class is going to return the maximum likelihood estimate as well as the value of the likelihood when computed with this maximum likelihood estimate. Now the small note about maximum likelihood estimation is that for certain probability models, certain simple probability models, they have a fit method. So again, I'm referring to what was said yesterday in distribution. So some of those probability models already have a fit method that does maximum likelihood estimation. So if this is the case, then we're just gonna call that fit method. If we have a more complicated model that doesn't have a fit method, or if we have a Python model that uses run model, then we perform numerical minimization using scipy.optimize.minimize. And here you can give some parameters, some options to the minimization procedure. For example, method optim bounds of x0. So here I'll let you go back and look at scipy.minimize. To see what those inputs look like. The other thing that we can do is that we can do several runs of the minimization starting at various random points. And for this, you can set the input iter optim to something greater than 1. And that means you would gonna run several minimization runs. So here is again, a summary of the input and output attributes of the ML estimation class. So again, the only two required inputs are the model and the data. And then you can give some extra parameters for that just govern the minimization process. And what we return are the maximum likelihood estimator as well as the value of the maximum likelihood, as I said. So it's the maximum likelihood estimation is pretty straightforward. The exact same, you call it the exact same way you would call any other class. And here I'm gonna go back to the examples to show you what it looks like. And so, so basically it's the same file that I was showing before. So getting back to first the probability model, the univariate Gaussian one. So I said I generated the data. I generated and instantiated my object of class model. And now I'm calling the maximum likelihood estimator here. So I give it as model, the candidate model that I was defining here, and then as data, the data that I self-generated myself before. And then I'm just printing the output. So this is this is very simple because the normal PDF that is defined within distribution already has a fit method. So in this case, the maximum likelihood estimation is just calling the fit method. So it's really easy. Now, the second one is the one with the Gumbel copula. And so if you look at, so if you look at the bivariate normal gumbel.py file, which is the one, the distribution that is being called by this model, you can see that it has a PDF log PDF method, but it does not have a fit method. So in this case, what maximum likelihood estimation does is that it performs a minimization procedure. And so here, so same idea as before, I'm calling maximum likelihood estimation by giving it the model and the data. And here I'm giving it also a set of a few other parameters to govern the minimization procedure. So I'm doing only one iteration of the minimization. I'm giving it some bounds so that it knows where to look for the parameters, and a method for the optimization. And as you can see, so here I'm just showing the results of that. But so the idea is that here it does run an optimization procedure because the distribution does not have a fit method. And finally, we go back to the regression model that was defined as a Python model that runs using run model. And again, it's gonna run a minimization procedure. So here I'm again calling maximum likelihood estimation. So here I'm not giving it any other input, so it just uses the default of scipy.optimize.minimize to perform the minimization. And again, you can see the fitted parameters here. Okay, so this was maximum likelihood. Now, so this was the first parameter estimation class that UCuPy has. Now you can see that what it does is that it gives you a point estimate of your parameter vector. So it gives you one value. Now, if you do, on the contrary, if you use a Bayesian approach, what you get out of that is a full distribution. So it's basically if you use Bayes' theorem, you can learn what's called the posterior PDF of your parameter, which is the conditional probability of your parameter knowing your data. So here you get a full probability distribution over your parameter. Again, what it requires, when you call that in UCuPy, what this Bayes parameter estimation class requires is an instance of class model, which is going to be your model and some data. And the code yields samples from the posterior PDF. And those samples are obtained by running either Markov chain Monte Carlo or importance sampling, which we saw yesterday. So if what the code does is that it defines a log posterior callable that computes this p tilde here, which is the log PDF of the likelihood plus the prior. So getting back to what we said yesterday from MCMC and importance sampling, we were defining this scaled p tilde, and so you can see how it appears here in Bayesian inference. Basically, this P of data here is called the evidence, and it's very complicated to compute. So you don't have access to actually the posterior. You just have access to a scaled version of it, which is p tilde. So just getting back to what we said yesterday. So in Bayesian inference, you need to give a prior, which is this P of theta here. If you do not provide a prior, we use an informative prior, which basically gives the same probability to every point in the domain. I would not recommend to do that. So if you have an idea of either bounds or any type of prior in your model, please provide a prior to your Bayes parameter estimation. And then the code is going to call sample methods.mcmc or sample methods.is from the sample methods that we saw yesterday. And this is governed by the input sampling method. So the default is MCMC, but you can choose whether it's MCMC or important sampling. So now if you do MCMC, as we saw yesterday, it requires a seed value. If you do not provide a seed value, the code is gonna first run maximum likelihood estimation in order to get a seed, and then it's gonna start running the chain out of that maximum likelihood estimate. And then you get samples from the posterior PDF as well as the acceptance ratio of the chain. If the input sampling method is important sampling, what you require is a proposal density. If you do not give a proposal density, what the code is going to do is that it's going to sample from the prior. So you need to give either a proposal density or a prior. Otherwise, you're going to get an error out of UCUPy. And then what you get out of that are going to be samples as well as the weights, which combined provide an estimate of your posterior PDF. So here is a summary of the parameter estimation class input attributes. So again, you require a model, some data. The sampling method, the default is MCMC, as I said, but you can set it to MCMC or important sampling. The number of samples that you want out of this procedure, it's another required input. And then, so if you define, if you want to use important sampling, you need to define the proposal, possibly the proposal parameters. While if you use MCMC, you need to define the scale, proposal type if you use NMH. So here I'm the algorithm jump and burn. So here I'm referring to what we said yesterday about the MCMC class. And again, the seed is only required for MCMC. If it's not provided, we're gonna run first maximum likelihood estimation. And the output, I've already talked about this. In both cases, you're gonna get samples of, so that's gonna be an array of size n samples times n params. In the case of important samplings, you're also gonna get the weights, and in the case of MCMC, you're gonna get the acceptance ratio of your chain. This class, so it's called Bayes parameter estimation. It's called in the exact same way as any other class in UCUPy. You give in all the inputs that you think are necessary. So here we have actually two examples for that. I'm mostly going to go through one, through the MCMC one, but basically we use the same models, the same problem as before, run Bayesian parameter estimation using both MCMC and important sampling. So I'm going to show you mostly the MCMC part. So again, it's just to show you the folder. It's in example Bayesian illustrations of inference classes, and then we have those Bayesian parameter estimation, MCMC or IS. So okay, so that's this one. So again, just recalling a little bit of theory here, we are computing the posterior PDF of the parameters knowing your data. And so here is the exact same problem as before. So first is a univariate Gaussian. I'm trying to learn the mean and the standard deviation of that model. So here you can see the difference in calling the model class, and the difference is that now I give it a prior. So again, model type is PDF, model name is normal, 2 parameters, but now I define a prior over my 2 parameters. So a uniform prior over the mean and a log normal prior over the standard deviation, which has to be positive, and then the prior parameters. And I call a Bayes parameter estimation using, again, my data and my model. The sampling method here is MCMC. The number of samples is also a required algorithm, required input, sorry. I define the algorithm, jump and burn, everything you need to give to MCMC. So I refer to MCMC for that. The PDF proposal scale here, you can see that it's the same dimension as the dimension of the number of parameters that I'm trying to learn. And here I'm showing you the results. So here, so this is where I start from. My seed was 1.2, something like that. So you can see the samples that I'm generating, and I can converge into the true solution, which is 10.1 here. And here you can see the approximate plots of both the prior in blue and the posterior PDF that I'm learning. Okay. And then the regression model, which is now, as I said before, a Python model. So here I'm generating data in the exact same way as before. And now you can see that I'm not giving a prior to my model, which means that Bayesian parameter estimation is going to run by assuming a non-informative prior uniform over the whole domain. And I call bias parameter estimation using the data, my model, again, MCMC. And again, you can see the convergence of the chain here, and here the posterior PDF. So the true value with which I generated the data was 1, 2. And you can see that I get posterior PDF that are highly peaked around those 2 values. And then the final thing that I can show is I've run diagnostics. We talked about it a little bit yesterday. Diagnostics is for MCMC and importance sampling, and they give you a little bit of an idea of how should you trust your results or not. So you can see the acceptance of ratio of the chain is actually pretty low here. If you look at the ESS is also pretty low. So actually in that case, you can think that would be better to run a few more runs of that MCMC in order to get a better approximation. But you get a feeling for the chain, the convergence, as well as the correlation between samples. So this is just running diagnostics for MCMC. And then, so I'm not going to go really much through that, but basically we've done the same for importance sampling. And the only thing that changes is that when you call bias estimator, then you set sampling method equals importance sampling. And so here, for example, I'm not defining a proposal, so I'm sampling from the prior. The other difference is the diagnostics, obviously, because now you have diagnostics on importance sampling, and what they do is that they again compute some kind of effective sample size, and they plot the weights, and so you can see that even though I generate 200,000 samples, the effective sample size is like 18, so you have actually very few weights. You can see those weights here. You have only few weights that have a significant weight, so actually many of your samples have almost 0 weight. So something to be careful about when you use importance sampling, and that's why we recommend using those diagnostics. So those were the two main classes for using parameter estimation. So here you're just learning a parameter out of your model. Now, the thing that's interesting is that you can do, here I've shown really simple examples, but you can do actually things that are much more involved. And so here I'm going to show you an example. So if you're on Binder, do not run that example because it takes a while to run, and also you need a package called SFEPy, which does finite element modeling for just finite element modeling. I don't know if it's installed. We haven't. It's not on Binder, so do not run that example. Just follow along with me, but. So here you need to go to, again, example Bayesian, and now it's in the folder more advanced examples and the parameter estimation one. So the idea here, the only thing that I want to show is that you can take an external code and very easily tweak it so that you can perform inference on it. So here I'm using a package called SFEPy that does finite element modeling, and in particular they had one example where they were doing a parameter estimation for a problem that I'm showing here. So basically it's so this is a microsystem here that is subjected to some tensile tests. Each point here requires running another finite element code which runs the microstructure that you can see here. And so this is a composite microstructure with a matrix and fibers. And the idea is that if we have some results of the tensile tests that are performed on the macro system, can we learn the parameters of the microstructure. It would be the Young's modulus and Poisson ratio of both the fibers and the matrix that you can see here. So I don't know if everybody's know a little bit about finite element. That's not really the problem. The idea is that this code was written by someone else, and I just took it and tweaked it a little bit so that I can perform inference with it. So basically, this code runs two different finite element models here. And within SFEPI, what they did is that they used some data. So here they have 4 data points, and they were learning the, so as I said, the 4 parameters that govern that microstructure here by just minimizing a certain function, which I'm showing here. So first, I'm basically redoing what they did in that code. But then, more interestingly, we're basically doing both maximum likelihood and Bayesian parameter estimation within UCuPy. So the idea here is that you can just define a model. So here I have 4 parameters. It's going to be a Python model. The model script and the model object name is what's going to go into run model. And basically those, you can see they are also in the folder, but they're just .py files that define a function, and that function is called one simulation. And actually the very first, the box 2 here, it just runs that function one simulation. And what it does is that it takes as an input the parameter vector, so the 4 parameters that represent the microstructure, and it turns out an output, which is the output of that tensor test here. So this is the only thing that one simulation does. So basically you just have to tweak your code to define that that function, one simulation here, and you can just define your model and run inference within UCuPy. So here we first perform maximum likelihood estimation, which is basically the same. I'm gonna let you read more in detail if you wanna see, but basically this is almost the same as minimizing that sum of squares here. So we get a result, which is just one parameter vector. But then more interestingly, you can look, for example, here, what we did is that we looked at the maximum, at the likelihood, so the probability of the data knowing your parameter. So for example, if you look a little bit at how the likelihood changes when you change the parameters, you can kind of get a feel for what are the parameters that influence your likelihood. So what are the parameters that influence your data, and so basically what are the parameters that you can learn out of that data. Because if your parameters do not influence your likelihood, then probably you won't be able to learn them. So for example, here, if you look at that plot, you can see that your likelihood is mostly, it's much more influenced by the matrix Young's modulus than by the fibers one. So you would be able to learn this parameter with much more confidence than the parameter that governs the fiber. And this is something that you can see if you perform Bayesian parameter estimation, because then you get a full posterior PDF for that. And so here, this is the same. We defined a model where now I also have to give it a prior. So you can see that I define a uniform prior over the 4 parameters. So this is why I have a slightly different model here. Again, I'm gonna let you read, but basically, I run Markov chain Monte Carlo simulation using different scale parameters so that you can see a little bit the difference between using different scales. So this is a scale that is much too large. This is much too small. So you can get a feel for how MCMC behaves with different parameters. But the most important is that you can get an idea of your posterior PDF of your parameters. And for example, you can see that you're able to learn that Young's modulus of the matrix with much more confidence than the one of the fiber. So this is the idea behind Bayesian parameter estimation. You can do, you can get a full posterior distribution, and so you can get more like an idea of the confidence with which you learn your parameters. And again, you can run diagnostics. So basically, the idea is that you can really take an external code, just tweak it a little bit so that you define this one function that's gonna go within run model, and then you can run maximum likelihood estimation, Bayesian parameter estimation using either MCMC or unimportant sampling. So that's really easy. So again, this code takes a while to run. So, and it requires the package SFEPy, which is an external package, but later on, feel free to download that and run it too. So those were examples of parameter estimation. So you have one model and you're trying to calibrate the parameter based on data. The last thing I'm wanting to talk about is this idea of model selection. So where you have set of candidate models. Each of them are parameterized, a different set of parameters, obviously, and you want to rank those models or choose which model is the best, how the model that best explains the available data. Now, in model selection, you have to penalize for models that are overly complex. Because you can have models that are extremely complex, then they're gonna overfit your training data, but they're not gonna be able to generalize to unseen data because it's just too complex. And so this is the principle behind Occam's razor. So the first way that UCUPy implements model selection is through information theoretic criteria, where here you can compute, for example, the AIC criterion. And then the model that minimizes that criterion is your best model. So you can see that all of those criterion, they have the sum of two terms. -2 log of the likelihood is a data fit terms. So it gives you an idea of how is that model capable of explaining the data. And then you have another term, for example, in AIC, it's 2k, where k is the dimension of the parameter vector, which basically this term grows as with the complexity of the model. So basically this term penalizes against complex models. And so you can try a different criterion, basically those criterion that differ in how they penalize complex models. And so you can see that the data fit term, it relies on it's the log of the maximum likelihood. And so you can guess that basically when we're gonna run this class info model selection, we're gonna use the maximum likelihood estimation class that we've seen before. So when you want to implement info model selection in UCUPy, you need to give it a method, which is basically which criterion do you use. And then the class is gonna call maximum likelihood estimation class to compute the value of the maximum likelihood. And so you can give, so all the inputs that are used within maximum likelihood estimation, you can give them to info model selection. So all those inputs, they must be given as a list that the length of that list is equal to the number of candidate models that you're ranking. So, so maybe I'm just gonna go to that next slide for one. The two required arguments for running info model selection obviously are the data, same as before, and the candidate models. So this now is not just one model, it's a list of instances of this model class. So now you have a list of models, and all the inputs to ML estimation, they must be list of the same length that the length of this candidate model, sorry. And the class is gonna output a certain number of outputs. So for example, the model probabilities, which I computed is shown here. The fitted parameter vectors, so the maximum likelihood estimates of all the parameters, of all the parameters of all the models. And you can define an input called sorted outputs, and this, so if sorted outputs is set to true, which is the default, the outputs are going to be sorted in a decreasing value of the probability shown here. If sorted outputs is set to false, then all the outputs are going to be returned in the exact same order as you gave them in candidate models. So it's just how are your outputs given. So again, for example, those are the inputs that you give to maximum likelihood estimation. And you can see that they have to be given as lists of the same lengths at the length candidate model. So I've been through that already. And so here are all the outputs that I was talking about. So models at the list, a list of instances of class model. You have the model names, fitted parameters. So the criteria as are, so AIC or BIC, whichever one you use. And then we're also returning the penalty terms, which is, so here, for example, the penalty terms for the AIC would be the 2K. So this is just for you to, if you want to have a look at how those criteria penalize for models, and then the output probabilities now. Yeah. Okay. As always, you import from UCuPy import inference, or UCuPy inference import info model selection as before. And here I'm gonna go through an example. So here we have to go again in Bayesian, illustrations of inference classes. And here it's gonna be the model selection info criteria. Okay, so here again, some imports. So now a slightly different problem. I'm generating data using a gamma distribution with a scale parameter 1. So I'm generating 200 data points. So this is a univariate distribution. So you can see the shape of the data here. And I'm comparing 3 different models. So those are probability models, like they're exponential, gamma, or chi-square. And basically the idea is that exponential, it has 1 parameter less. Gamma and chi-square both have 2 parameters, but they actually are equivalent for the parameter I'm looking at. So here you see that I have to define, for all of those models, I have to define an instance of class model. So those are probability models, so I have to give them this model name here, model type is PDF, and the number of parameters. Sorry, exponential has 2 and the other 2 have 3 parameters. And then I create a list of candidate models which gather all those instances of the class model. And then I perform info model selection. So here you can choose whichever criterion you want. Here I tried 3 of them, but I'm only, no, actually I'm showing all of them. So you have to give it the candidate models, which is the list of candidate models, obviously the data, the method is the criterion, and then I sort the outputs according to the output probability. And so here you can see, as I said, the chi-square and the gamma are actually equivalent here. It's basically the same model, just a different parameterization. But the exponential, it has 1 parameter less, but it's actually not able to explain the data. So for example, yeah, so you can see here that it shows us the chi-square and the gamma. Basically, it has the same value of the criterion, and the exponential has a higher value of the BIC, so it's less probable. So it's less able to explain the data. Okay. The other example here is the this regression type problem that I was looking at before. So again, I generated data from the quadratic model, same thing as I did before, the Python model. But now I'm comparing 3 different functions, either a linear function, a quadratic function, or a cubic function, and say which of those functions is best able to explain the data. So again, I defined those 3 different models, and I create a list of candidate models. So now the model type is Python for all of them. The number of parameters are either 1, 2, or 3. Otherwise, it's the same as before. And then I perform info model selection here. So again, giving it the set of candidate models, the data, the method that I use is BIC. And so here, so it's going to run maximum likelihood estimation using the optimization procedure. And so I choose as an optimization method this method here that's going to be called by SciPy, that optimize and minimize. And you can see that the method optim is given as a list. So the ×3 here means that it's a list of length 3, which is the same as the number of models that I have. And here I'm printing the results. So basically you can see that what happens is that it chooses the quadratic model as being the best model, then cubic, then linear. What's interesting here is to look at the penalty term. So you can see that the penalty term is the highest for the cubic model because this model has the highest number of parameters and the lowest for the linear. And actually, so here what I did is that I plotted the function using the maximum likelihood estimate that was fitted to the data, and you can see that basically the cubic and the quadratic function they are able to both fit the data well. So it's able to obviously find a set of parameters that's able to explain the data. The linear doesn't fit the data at all, but the quadratic model is chosen because it's the less it's able to explain the data, and it's less complex than the cubic model. Which is true because this is how I generated my data using that quadratic function. And so just to so in this PFN models, this is where I defined all my functions that are called by run model. Okay, so this is model selection using information theoretic criteria. And the last class, we're almost done, is to do model selection within a Bayesian context. So here what you do is that you compute the posterior probability of your model knowing your data. So now this computation requires computation of the evidence, which is this term here, and it requires an integration over the parameters. So this is actually really complicated, sorry, to compute. So for now, the algorithm that we have, it uses the harmonic mean estimator to compute that evidence. So I'm just gonna say you have to be careful with that because it's known to yield results that have really large variance. So when you rerun the thing, it may have quite different results. And actually, if you run the examples, you're going to see that. So this is going to be improved upon in actually V3, not V2, sorry. So we are working on that. But so you can start to try it out, but I would just say be careful about the results that you get out of that. Out of those runs. And so basically what happens is that this estimator here, it uses sample from the posterior PDF. And those samples, we obtain them by running MCMC. So again, the base model selection class is going to call the bias parameter estimation class with MCMC that I talked about before. And so I'm not going to spend a lot of time on this because it's exactly the same as what I said before. You need to give a candidate a list of candidate models and all the inputs that you can give to bias parameter estimation. You can also give them to bias model selection, and you have to give them within lists that are the same length of the number of models that you have. So it's really similar to what we had before. So you need to give that candidate models data. In addition, though, you can give them prior probabilities. So those prior probabilities are the prior probabilities of the model. By default, they're going to be equals to 1/m, where m is the number of models. So each model is given the same prior probability by default, but you can change that if you want. And otherwise, so the number of samples is also required. All those inputs here are used by Bayes parameter estimation. Okay. Now the outputs of that are again the models, model names. Now we also output the evidences, the posterior probabilities, obviously, which is the the most important thing you want out of this, as well as the MCMC output. So this allows you to plot the posterior probability of your parameters if you want to have a look at that. And again, they're going to be sorted either in the same order as what you gave in the list candidate models, or by decreasing order of the posterior probabilities depending on the input sorted outputs, whether you set it to true or false. You call that class in the exact same way that you called any other class, by giving it all the inputs that it needs. And this is the last example that I'm going to show. Again, I would advise you not to run that example, because it takes a while to run, because it runs MCMC for several models. So again, in the folder example Bayesian, illustrations of inference classes, it's the Bayesian model selection. And so basically here, I'm gonna let you go through it, but this is a Python model where I'm comparing, again, this linear versus quadratic versus cubic functions. And the good thing about this is that you can actually compute the true. So if you give a prior, a Gaussian prior for all the parameters, you can actually compute the true value of the posterior PDF for all the parameters and the true value of the evidence. So the idea is that it's a way that you can kind of check out a little bit your results. So so this is the analytical derivation here. So here the data that I generate is from the quadratic model. Same as before. My data, so I'm putting the data here, which is a one-dimensional vector as before. And here I defined my models. So so yeah, I do quite a lot of computations here. I don't need to, but where do I call my model? Well, somewhere here. Sorry, Mela. So I'm doing a lot of computations here. So this is, again, this refers to my analytical derivations. I was just trying to find where am I calling my model, and it's basically, so so it's here, I call model for the 3 models, and I create a list of candidate models. So here I'm going through the same script as I showed you before. And the model object name is either linear, quadratic, or cubic, and it's going to point to a given function within that .py file, given the number of parameters. And the prior, basically the prior is multivariate Gaussian, and given a certain mean and standard deviation. So first, those 3 things, they run MCMC. So bias parameter estimation, so you can, and I'm showing the output, so you can see an idea of the prior, the posterior. So again, because this is an analytical example where we have access to the true posterior, so we can compare what's the true posterior versus what bias parameter estimation gives you. So here the cubic model has 3 parameters. So you can get an idea of how MCMC performs. And here I run Bayesian model selection. And so I give it the data, candidate models, and so yeah, so all the inputs of bias parameter estimation, so they're given, they're defining here, and you can see that they're always lists of length 3. So for example, the number, so in the, you know, in the smaller problems of 1 parameter, I use less samples than in the larger problem. So all those are inputs to MCMC and to bias parameter estimation. So again, this takes a while to run, so, but basically at the end of the day, you get an idea of the evidence and the probability. So here I chose the model quadratic as being the right one, but with the posterior probability of 0.64. But again, I would be very careful in how you read those results using that harmonic estimator, mean harmonic estimator, because it's not the best estimator out there. So we're gonna improve upon that. but at least you can start doing some Bayesian model selection using that this problem. So this is this was inference, and I think that now we were planning on doing a little break of like 15 minutes, and so that leads us to 10:25.